Hopefully, at this point, you're reasonably comfortable with the idea of simple linear regression. So I have a predictor variable and observations of that. I have a response variable and associated observations of that, and I can explain the relationship between the two. But we can also have multiple linear regression where I have more than one predictor variable trying to explain the response. So the model looks similar, a simple straight line model, but where I've got more predictors, it's a little bit messier notationally, because if I've got n observations of k predictors, I need two subscripts on the x's to state which observation number is it of which predictor. So this model looks similar, like yi is an intercept term alpha, plus the slope beta 1 associated with the ith observation of x1, or multiplied by that to get the ith predictor, to get the ith response, plus beta 2, the slope associated x2 with the x2 variable, so plus beta 2 times the ith observation of x2, so plus beta 2 x2i, and so on. And I've still got the exact same, I suppose, machinery to fit it, but I fit this by setting the sum of the residual errors to 0, and that I minimize the sum of the squared residual errors. So the idea is the same, except for the fact that the notation is a bit messier, and that rather than having to differentiate with respect to the slope beta, I have to differentiate with respect to each of the slopes, beta 1, beta 2, beta 3, up to, got k predictors, up to beta k. So when I say the theory is the same, that's true, but that doesn't mean the implementation isn't a lot messier. But this is where a little bit of relatively simple matrix algebra can, I wouldn't say make the calculation easier, but make the calculation tidier. What I can do is, if instead of writing down all of these different equations that I have to calculate by differentiating with respect to each variable, I can write down one matrix equation. So I'll define a vector y being a set of all of these observations y1, y2 to yn. I'll define a vector beta being a vector of all of the parameters I need to estimate. So that's the intercept term alpha, and then the beta 1 to beta k, the k slopes. Now, the x of observations is the slightly tricky one here, because it's easy to see that I need each of the observations in there, x11, x21, x31, xk1, but I also need this column of ones at the start, and that's because in the model I want plus one lot of the intercept term. So you can see when I multiply out the matrices that this column of ones at the front of the x's is always multiplied by the first term of the beta vector, so it just says plus one lot of alpha. Here I am going to do some distributional assumptions. I'm going to assume that the residual errors are normally distributed with zero mean and with constant variance, sigma squared. And by setting this variance covariance term at the back of the epsilon matrix to be an identity matrix only has a constant down the diagonal, one down the diagonal, and zeros everywhere else. So what that's saying is that the residuals are drawn with constant variance and no correlation between them. So that's the first time we're starting to introduce some distributional assumptions. Starting with this, y is the matrix X times the vector beta plus epsilon. We can multiply on the left by X transpose. Then just a simple rearrangement, taking the X transpose epsilon term to the left. Then we can then invert this X transpose times X to get the beta, because what I've got is I've got X transpose X beta on the right, which I don't want. So if I just take it over to the other side, I can multiply both sides by X transpose X inverse. So I can then optimize that when X transpose epsilon is the zero vector, and that should be the case since the residuals are unrelated to X with mean 0. So when I've set that term to 0, I will get that my estimate beta hat is X transpose X inverse times X transpose Y. So this looks a lot like the statement that we got for the simple linear regression, where I got the beta hat was the sum of X minus X bar times Y minus Y bar divided by X minus X bar squared. So you can see the analogy between the two forms, but this is the multivariate cousin. Let's apply this to a simple data set. So here I've got 5 observation points. I've observed when x1 is 1 and x2 is 1, y is 3. When x1 is 1 and x2 is 0, y is 6, and so on. The first thing I need to do is define the vectors and matrices. So I have 5 observations of y, so I line those up in the vector y. I have 3 coefficients I wish to estimate: alpha, the intercept, and 2 slopes, beta 1 and beta 2. I then need to line up the x's. So I line up x1 in one column, x2 in another column. But before that, I need the column of ones to say I want one lot of the intercept in each calculation. So now this is more where I would use a computer to calculate some of these. Not that we can't do matrix multiplication by hand, but that for larger models, this is going to get very slow and very messy very quickly. So I multiply X transpose Y, what I get is 37, 76, 21. Please feel free to check any of those. And X transpose X is a little bit messier, but of course a 3 by 5 matrix multiplied by a 5 by 3 will give me a 3 by 3 matrix. If I've got X transpose X, then X transpose X inverse. Again, please feel free to verify that. Just check that multiplying those two matrices together should give me the 3-dimensional identity of 1, 0, 0, 0, 1, 0, 0, 0, 1. The beta hat is X transpose X all inverted times X transpose Y. I've worked out X transpose X inverse. I've worked out X transpose Y. So putting all of that together will give me 2, 4, minus 3. So in other words, that tells me that my estimate of the coefficients will give me that the intercept term is 2. The slope on the x1 variable is 4. The slope on the x2 variable is minus 3. So that's my model, and in fact, I just made those numbers up as I was writing the slide. And in fact, that model fits absolutely perfectly. There are no residual errors. Each of the y's is exactly 4 times the x1 variable minus 3 times the x2 variable plus 2 with no residual error. Obviously, in general, you're very, very, very unlikely to see a model with no residual error, but that's what we have here. For the multiple linear regression, we did introduce some distributional assumptions that the errors were normally distributed, constant variance, and uncorrelated. Now, we can actually fit some more complex models by relaxing those assumptions, or indeed introducing other assumptions. So, like time series models, where I have an inherent ordering of the terms, that the second observation happened after the first but before the third. Or multi-level models, where I've got some grouping effects. For example, if I look at students' attainment in a school, maybe the students are in a class who might all have some similar trend. The classes are within a school that all has some similar trend. So I can fit more complex model structures via the same sort of idea. But if I've got some term here where I'm saying the residual errors are not necessarily uncorrelated, that rather than saying I have sigma squared times an identity matrix, I've got sigma squared times some variance covariance matrix, where potentially I have covariances between the residuals. And what I can do here is I can do the same sort of argument by just multiplying by the Vn to the minus a half, so effectively the square root of the inverse of the variance covariance matrix. And when I do that, I will get to a form where I get a rotated or a changed y is a changed x times beta plus a changed set of residuals, which in fact are uncorrelated. So in other words, I can fit more complex models just by acknowledging what structure I think the variance covariance matrix has and then adjusting accordingly. What I've got is if I've got the same thing here, but instead of my original y and my original x, I've got the tweaked versions to acknowledge a different variance covariance structure. I can then estimate the adjusted y accordingly, and hence the beta for that. And all I need to do then is adjust it back to the original scale. So the same machinery can fit the model with the simple assumption of uncorrelated errors, but with only a minor tweak can fit many more complex models as well.